Okay, so in our first example, we're going to be looking for the area of the part of the surface 2y plus 4z minus x squared equals 5 that lies above the triangle with the vertices 0, 0, 2, 0, and 2, 4. So in order to do this, we're going to start by taking a look at the region that we're integrating over. So the region D that lies in the xy plane. We begin by finding those vertices. So we have a vertex for this triangle at the origin, 0, 0. We have one at 2, 0, which would be here. And then we have one at 2, 4. So let's put 4 up here. Creates this triangle, which we're going to call D. Okay? Now, before I go to my surface area formula, I know that I'm going to be integrating over this region. So what I want to do is come up with a way of describing this region as a set, either as a type 1 or a type 2 region. This is a very straightforward type 1 region. My function giving me the graph on top of this type 1 region would be y equals 2x, easy enough to find using the point slope form of the equation of a line using these 2 points right here. The lower function down at the bottom is the graph of y equals 0. So any point in the region D is going to have a y coordinate somewhere between 0 and 2x. So now I'm going to set up D as the set of all x, y, such that x lies between 0 and 2. That's going to be my fixed interval or my constant interval. Y is going to be between 0 and 2x. Okay. Now I know that in order to use my surface area formula, I need my partial derivatives of z of the function that gives me the surface I'm considering the surface area for, both with respect to x and with respect to y, and those show up in that formula. So in order to do that, I'm first going to need to isolate the z in this equation so that I can take partial derivatives. If I were to do that, then my equation will end up looking like z equals 1/4 x squared minus 1/2 y plus 5/4, like this. Okay? Now, the next thing I want to do is find those partial derivatives. So my partial derivative of z with respect to x is very easy to find for this function. It's just going to be 1/2 x. Okay, and then my partial with respect to y, looking at this function, would be negative 1/2. And now all I need to do is find my area using that double integral formula. So move this up. The area of my surface is equal to the double integral over D of the square root of the sum of the squares of the two partial derivatives I just found. Partial of z with respect to y here, plus 1 dA. All right, so I want to find, or I want to plug in the partial derivatives that I just found. So I'm going to square this, I'm going to square this, I'm going to add 1. That's going to look like the partial derivative. And in fact, since we've already described the region D, let's also go ahead and set this up as a type 1 iterated integral. So we're going to have 0 to 2, 0 to 2x here, and then square root of, if I square my partial with respect to x, I'm going to end up with a 1/4 x squared. If I square my partial with respect to y, remember that was negative 1/2. Squaring that gives me 1/4. and then plus 1. And remember, it's a type 1 region. These represent bounds on my y, so the inner integral is with respect to y, outer is with respect to x. If I were to add these up, I would get 5/4, these two constants. I could take a 1/4 and factor it out. When I take it out of the radical, I'm taking its square root, making it a 1/2, and that could be brought all the way out. So I could say that this is 1/2 times the integral from 0 to 2, integral from 0 to 2x, and then what would be left in here is x squared plus 5 dy dx. I'm going to be careful here because at first glance this may seem like a difficult integral to do. If you're just focusing on the integrand, you might look at this and think, oh, that's the kind of integrand I would need some kind of a trig substitution for, or something like that from Calculus 2, when in fact we actually don't, because remember, we're integrating with respect to y, not x. So even though this is usually kind of a difficult function to integrate, it doesn't matter because the whole thing is being treated like a constant. So this is going to give me 1/2 times the integral from 0 to 2 times square root of x squared plus 5 y from 0 to 2x dx. Okay, now let's think about what happens here. I'm plugging these in for y, not x. So if I plug a 2x in, then I'm going to get a 2x times the square root of x squared plus 5. Plugging a 0 in, the whole thing goes to 0. So all that really matters is the 2x. Notice that the 2x that's going to show up here, the 2 as my coefficient could cancel with that 1/2 right there, simplifying the notation a little bit, or simplifying the expression, I should say. So this becomes the integral from 0 to 2 of the function x times x squared plus 5 dx. Okay? This can be evaluated using a fairly straightforward u substitution. X squared plus 5 is my u. I'll let you fill in the gaps here with the u substitution. What we should end up getting as a solution to this one is 9 minus 5 to the 3/2 power over 3. Okay? That's going to be the area of the surface over that triangle. I didn't have to sketch the surface in this case because I was able to just work with the region that I integrated over. But in my next example, it's going to be important that we try to sketch the surface as best we can. So this is our second and final example for this section. This time I want to find the area of the part of the sphere shown here that lies inside the paraboloid z equals x squared plus y squared. This is tricky because it's not giving us a region in the xy plane explicitly. We have to do some work to figure out what the region D looks like. So we start by trying to sketch both of these surfaces in 3 dimensions. First thing I want to do is notice that this equation is the equation of a sphere, but it's not the standard form of the equation of a sphere. If you were to subtract the 4z over and then complete the square with the z's, you're going to see that this could be written as x squared plus y squared plus z minus 2 quantity squared equals 4. I'm going to let you determine how I got that. But that's going to be a little bit more informative as far as how we sketch this surface. So I want to attempt to sketch this thing, and I fully expect this picture to be terrible. So hopefully you can make sense of my drawing here. Okay, so what we have here is a sphere that's centered at 0, 0, 2, and it has a radius of 2. So that's 2 on the z-axis. I'm going to go 1, 2. There's 2. And there's the center of that sphere. In addition, its radius is 2, so it's going to reach down as far as the origin and reach as high as 4 up there. In addition, 2 units to the right, 2 units to the left, 2 units back, and 2 units forward. So all directions using the x and y coordinates, or x and y axes. I want to try to come up with labels for those, and hopefully this thing does look like a sphere when I'm done with it. 1, 2, that's -2 back there. 1, 2, this would be 2 up here. Okay, so center I can already tell it's not going to look great. I should have a point out here, and it's going to look something like this. This is basically its trace in the YZ plane. Let me label these. Okay. In addition, my negative 2 back here and my positive 2 back here, if I move from the center kind of out to those points, it's not going to look great. That's okay. This is kind of like the trace in the XZ plane. So it doesn't look too spherical, but that's supposed to be a sphere, so just try to imagine it that way. And then in addition to that, we have this paraboloid, z equals x squared plus y squared. The trace in the xz plane, which is where y equals 0, would look like z equals x squared. The trace in the yz plane, which is where x equals 0, is going to look like z equals y squared. So I want to sketch those traces as parabolas. Those are going to look like this. Okay. And then I'm going to have another trace out here. Let's see if I can. Okay, so that looks pretty bad. But the important thing, if you can make sense of any of this, is that the paraboloid, if I were to slice it using any plane that's parallel to the xy plane, it's going to create a circle here. Any cross-section of this paraboloid parallel to the xy plane is going to be a circle. Now, if you read the description of this, it says find the area of the part of the sphere that's inside that paraboloid. So you notice that the paraboloid it shares a common point down here at the origin with the sphere, but then it lies inside the sphere until it eventually breaks out of that sphere. So there's going to be a curve of intersection between the sphere and the paraboloid, and it's that curve of intersection where the parabola breaks out. Once we get past that curve of intersection right there, notice that there's like the top portion of this sphere that lies inside the paraboloid. That's what we're trying to find the surface area of. So this little cap, if you will, of that sphere that's inside this paraboloid. So in order to determine the region in the xy plane that we integrate over to determine that surface area, I want to figure out what this circle is up here and project it onto the xy plane. So that's a curve of intersection. We've dealt with those before. We use the equations of the two surfaces that we have here to try and find that curve of intersection. So here's how I'm going to do this. If I notice z equals x squared plus y squared, and I get an x squared plus y squared also showing up in this equation right here. That's a great place for a substitution. So if I substitute z in for the x squared plus y squared here, I'm going to get z plus z squared equals 4z. Or equivalently, z squared minus 3z equals 0, or z times z minus 3 equals 0. Okay? Now, if z is equal to 0, that's down here at the origin, and that's one point of intersection that we know that these two surfaces have. That's not the point. That's not the place where we're looking for our region. We want this circle. So this circle, even though I didn't draw it totally accurately, it's where z is equal to 3. So I can alternatively think of that circle as the intersection of the plane z equals 3 with the sphere shown here. Or if I want to, I could take z equals 3 and substitute it into this equation, giving me x squared plus y squared equals 3. And that's actually what the equation of this circle would look like if I projected it down into the XY plane. So I'm going to draw that separately. Notice it's a circle centered at the origin where the radius is root 3. And that's going to be the region that I call D. Okay? Because we're integrating over a circle, and I know that I'm going to want to use a double integral over this region. This is another region where we would definitely want to be using polar coordinates. So I'm going to describe D in polar coordinates. D is equal to the set of all r theta such that r is between 0 and root 3 and theta is between 0 and 2 pi. Just barely squeezed that in there. Okay, I'm running out of time for this video, so I'm going to use my setup here in the next video to solve this problem.